man, I made these brilliant notes. The students are going to love this. Look at that. I put a box around the initial pH. This is going to be amazing. Okay, well, I better go down into my basement. What the heck? Charlie? Hey, oh, hey, Barney. Oh, hey, Barney. Yeah, I'd like to go to Turnip Festival. Is it okay if Dave came? Okay, yeah, it's a virtual event, and we're going to do it in your living room. Even better, he would like that. Okay, I'll see you in a little bit. Oh, had to invite a buffer person. You know, you need a buffer person sometimes. And if you don't need one, that means you're the weird guy. All right, I better go down and do the video about buffers. Hey everybody, hey, Mike here. I'm back from the virtual Turnip Festival with Barney. I'm glad I invited Dave along. Boy, he's a good buffer person, because Barney starts getting along with his conspiracy theories, and he believes all fruit is flat, ironically. I don't know. So anyhow, we're going to talk today about, like, you know, having a buffer person. Acid and base buffers are systems which don't change much. They change a little, but they don't change much in pH when an acid or base is added to it. So I want to do this thought experiment here. We're going to take pure water. Let's take a liter of it to make the math simple. And we're going to add a drop of concentrated HCl. Now, HCl is a strong acid, so we're making this simple. You may have seen the blue bottles of strong HCl in the laboratory. Well, you know, if we say a drop is about a 1/20th of a milliliter, that's a kind of a loose rule of thumb. And then we say, okay, how many moles per liter of acid would that be, and what's it going to do to the pH? Now, if it's pure water, it's going to be pH 7. And you might say, I might change it a little bit, the pH. You'd be surprised. So here's the thing. If we add the drop, and we say molarity times volume is moles, that's 7.0 times 10 to the minus 4 moles of HCl, which will then in turn produce H3O plus. And you might say, well, that's not very much, but let's go ahead and take a negative log of it. So we take that number of moles, H3O plus, take a negative log. I'm trying to keep the punchline out of it. And that's a pH of 3.15. One drop of concentrated HCl knocked the pH down 4 points. And you say, okay, that's just 4. That's not much. Remember, pH is logarithmic. That means that's a 10,000-fold change. And so water doesn't have any ability to fight off acid and base, or any ability to neutralize acid and base. And that's where a buffer comes in. Now, the reason the pH of your blood isn't changing wildly as you breathe, or as you go walk up the stairs or something like that, is because your blood has a buffer system that we will talk about later based on carbonic acid. And so here is what a buffer solution is. An acid-base buffer solution is a weak acid and its conjugate base, or a weak base and its conjugate acid. Now keep in mind, what if we wanted to, you know, sort of smooth out the change in the water? You could say, hey, I could put an acid in it, and that would, then we could add, we could put a base in here. Well, that would drive the pH way up to 11. And so, you know, acids and bases that are conventional acids and bases, they would neutralize each other too. So they can't cohabitate with themselves. So weak acids and bases, on the other hand, and a weak base and its conjugate acid, or a weak acid and its conjugate base, they're consequences of each other, so to speak. So let's take a real easy example, which we're going to do a calculation with in a little bit. Let's take the weak acid, acetic acid, and its conjugate base, acetate. Now, by the way, you can't just go put that in solution. You'd have to use a salt of it, like sodium or potassium acetate. But let's take a look at what would happen if we added acid. If we added acid, the acetate part of the buffer, keep in mind these both of those have got to be in there together. The acid would then be neutralized by the acetate part of the buffer, which would make something weak, acetic acid, and water. And so we would have dissipated all that H3O plus and turned it into something milder, like a weak acid and water. Or if we added OH minus from a base, then the acid part of the buffer would react with OH minus, making something mild like acetate ion and water. And so that's generally how a buffer solution works. The thing is that all buffer solutions are going to sit at a different pH though. So it turns out that the pH of your blood's roughly 7.4. And so the pH of this buffer solution, because it's based around a strong or weak acid, might be something like around 5. And so let's next calculate what is the pH of a buffer solution. Example problem, boop, boop, example problem, boop. So here's the thing, we're going to go ahead and we're going to calculate what is the pH of a solution of what we kind of described earlier. 10th molar acetic acid and 10th molar sodium acetate, which of course you know would dissociate and make something that, if you remember last video we did, something neutral, which doesn't matter, just kind of sits there as a spectator. But then the real important part of the buffer, the other half that's important, would be acetate ion. So this would really be 0.1 molar in each. We're only going to pay attention to the part of the buffer that really is doing the acid or base neutralizing. So now this is going to look weird. Here's our rice table. And what we're going to do is we're going to go ahead and for initial we're going to go 0.100. And then over here, we're not going to put water in the case, so we just leave it out. 0 and 0.100. Oh boy, you mean we're starting with both? Yeah. Which way's the equilibrium going to go then? Towards 0. Can't have any 0 in an equilibrium, so this is going to go to the right, and we're going to make plus x and minus x. Look familiar? And now it's going to set up just the same way it's always done for us. And so this would be minus x in the change line, plus x, and then plus x. So that at equilibrium, this is going to be 0.100 minus x, x, and 0.100 plus x. Oh, and by the way, the Ka of acetic acid, we're going to go look that up. The Ka of acetic acid is 1 times 10. Oops. There's different ways to write acetic acid, by the way, I should mention. That's one way you can write it. It's just different ways where you put the H on the right or the left. Some of the organic acids, they put it on the right. 1.8 times 10 to the minus 5. Thanks to our handy dandy Ka chart. Now what does that mean? Ka equals 1.8 times 10 to the minus 5 is going to be products over reactants. So x times 0.100 plus x divided by 0.100 minus x. Uh-oh, we're in trouble, folks. That's going to be a messy, messy, messy. Nope, nope. Remember, the small x approximation, 100 times rule, whatever way you want to look at it. The x next to that 0.1 and the x next to that 0.1, doesn't matter if it's adding or subtracting. If that's 100 times greater than Ka, the 100 times rule can be invoked and we can get rid of the x, and boy is that going to really make things easy for us, huh? So let's think about it. 1 times 10 to the minus 5, let's call it that, would be 10 to the 4 smaller than 0.1. So that's a hell of a lot different than 100. So this is way more than 100 times bigger than Ka, which means I can get rid of that due to the 100 times rule like we talked last time. Oh my goodness, look what else we can do. Now that just ends up being x times 0.100 divided by 0.100, and the 0.1, so x is just 1.8 times 10 to the minus 5. And I'm a negative log away from knowing what the pH is. So x is going to be the H3O plus, from the way I set up my ICE chart. And that is 1.8 times 10 to the minus 5. And so minus log of 1.8 times 10 to the minus 5 is going to be my pH. Let's figure out what that is. 1.8 times 10 to the minus 5. And then I hit the log button. I get 4.74 is my answer. And frankly, if it's a weak acid and it's conjugate base or a weak, you could set up that kind of buffer problem with an ICE chart, and you'll always have the 100 times rule because it's weak. So that's the thing about a buffer solution, is this greatly simplifies where you got a double 100 times rule. You have one in the numerator and one in the denominator. And now that makes for a little bit of simplification that we'll talk about next. But before we do that, I want to say that this buffer solution, if you added acid to it or base, it would change a tiny bit, because what that would end up doing is changing these ratios. Let's say you neutralized 10% of the acid, then that would be like 0.09, that'd be 1.1, 0.11, and you would slightly change this, but it wouldn't really change a lot, like 4 pH units, like when we just added acid to water. So there's a simplifying equation that's only used for buffer solutions because of this whole double 100 times rule thing. So let's talk about that next. All right, okay folks, you know how I'm always annoyed by how science names things after names of people all the time. So when you see the word buffer, think of this as the buffer equation, but it's named after two people. It's the Henderson-Hasselbalch equation. And it is for buffer solutions. And so what it is really just a restatement of Ka. So here's Ka for anything, weak acid. What if we were to go and try to figure out what is the pH of a buffer solution? So this is buffer solutions, but specifically relating pH and concentration, like we just did in the last example problem. So, okay, here's Ka. I'm going to try to go slow, but I don't want to write all this out because it's going to be boring. If I rearrange Ka where I get H3O plus by itself, then I have that where I take H3, I have to divide both sides by A minus and multiply both sides by HA, and I would get that. H3O plus is Ka times HA. Now HA is just a generic form of the acid, okay? And the A minus is the conjugate base. Now, that's H3O plus, which is related to pH, so what if I take the negative log of both sides? Well, the left side will end up being pH. And so the negative log of H3O plus. And now I take the negative log of that big old thing here, Ka times HA divided by A minus. Now, I don't want to get so mathy on you here, but it turns out that the rules for when you take logarithms of things, you can split these out. If you take the log of something that's multiplied together, you can take and split this out to be like minus log of Ka minus log of HA over over A minus. And so that's part of the rules, and what you can do is now, of course, minus log of H3O plus is pH. And minus log of Ka is something we call, that's a p function, minus log. This would be a p function of something else, but this is called the pKa. And if you take biology, they talk about that a lot. And so that's one way to quickly, with a very simple number, say what the strength of an acid is. And so the smaller the pKa, actually the bigger the Ka, that kind of thing, because the negative log tells you that. And the bigger the pKa, the weaker it is. But nonetheless, this is called pKa. You just go and take the number out of the chart and you take a negative log of it. And this is minus log of HA over A minus. So we'll simplify. That's called pKa. Let's actually get the negative out of the equation, because people don't like negatives too much in their equations. And this, my friends, is the Henderson-Hasselbalch equation. And I wouldn't balk at it, because it is a pretty handy tool. Think about that last thing we did, where we say, okay, we got 0.1 of each of these. Well, that would be a log of 1. The whole thing falls out. pH equals pKa. You go look up the Ka, the pKa of acetic acid. It's 4.74. Problem solved. No ICE chart necessary. And so that's the thing with buffer solutions, is because of that simplification. Whenever you see the word buffer, this is our next weapon right here. The Henderson-Hasselbalch equation. All right, let's put it to use a couple times in a practical way. Let's talk about why the pH of human blood can be maintained around pH 7.4. All right, let's put our nice fancy new shiny equation to use, where we're going to go and solve a buffer problem with it. So this is actually something that's pretty darn important. So I want to write out what goes on here. One of the things that happens in your blood is you generate carbonic acid. So right now, your cells are producing CO2, and one of the reasons that CO2 dissolves so darn good in water is because of its London forces, of course, but also because it makes this acid, carbonic acid. So actually, you'd think, oh, CO2 is garbage, I got to breathe it out. No, if you breathe it out too fast, you'd mess up your pH, and you'd be getting rid of the acid part of the buffer. And so you got actually a buffer system in your blood, the carbonic acid, bicarbonate, I should say, buffer. And so I looked up the Ka of H2CO3, and we're going to go and we're going to use the Henderson-Hasselbalch equation, where I'm going to go and I'm going to write this down, except I'm going to go put the individual components in it. So pH equals pKa plus log of HCO3 minus divided by H2CO3. It's always the thing with more H's on the bottom and the thing with less H's on the top. And I'm going to go ahead and I'm going to do the negative log of the Ka that is in most Ka tables. It's actually not in the one that I use, because mine's pretty not incomplete. It fits on one page. So let's go figure out what the pKa is. 4.3 times 10 to the minus 7. I'm going to take a log, take the negative of that, and I get 6.37. Now, they gave us the pH 7.45, so given was 7.45. The pKa is 6.37 plus log. And actually what they want is the ratio. So this will be pretty easy. I'm just going to solve for what's inside the logarithm. And now, if you had equal parts of bicarbonate ion and carbonic acid, this would fall out and become 1, and the log of 1 is 0, and then you'd have a pH of 7.45, or excuse me, 6.37. You'd have a pH of the pKa. Now, this is actually a number that is bigger than the pKa, larger, and that tells me that this ratio must be greater than 1, actually more than 10 times greater than 1, more than tenfold, because if it was a difference of 1 in pH, that would mean a 10 inside that term. So I can tell by looking at it thus far, because the pH of human blood is greater than the pKa, I can tell there's a lot more bicarbonate ion than there is carbonic acid, and it's actually almost a factor of 1. A difference. And inside a logarithm, 1 means 10 and 2 means 100. And you know, usually a buffer solution has roughly equal parts, but it doesn't have to have equal parts of both. So I'm going to clean this up, and I'm going to go ahead and I'm going to take and subtract 6.37 from both sides. And of course that would fall out on the left and on the right, and then 7.45 minus 6.37 would be 1.08 is going to be equal to what? 1.08 is equal to the log of HCO3 minus divided by H2CO3. Now here's the thing. How do I get inside that logarithm? I do a inverse log, or otherwise known as a 10 to the x. So I'm going to do 10 to the 1.08 on this side, and that's going to get rid of the logarithm on the other side. And now if it was 10 to the 1, that would be a factor of 10 when I do the 10. 10 to the 2 would be 100. 10 to the 0 would be 1. So let's go get our handy dandy calculator. Actually, I got 1.08. And I'm going to go second function, hit my log button, 12. Let's call it 12.0. So the ratio of bicarbonate ion to carbonic acid in your blood is 12, meaning we didn't even find the concentration. We just know that bicarbonate ion's 12 times more concentrated. As a matter of fact, the funny thing is it doesn't matter what each individual concentration is. This could be, you know, 1.2 moles per liter and then 0.1, or it could be 0.6 moles per liter and 0.05, as long as it's a 12 to 1 ratio. And now you could go, and I'm not going to get all biology on you. Why does your buffer system in your blood have more base than acid? Well, I can think of more acids that your body would need to guard against. Imagine if a pterodactyl ran after you and you had to run away, and you'd be producing lactic acid, and the pH of your blood would go down through the floor. And then you would encounter a condition called death. Because if you go more than a half pH point on either side, you're not just in alkalosis or acidosis, you're in dead-osis. I just made that term up, dead-osis. And so that's the thing. We have more acids to guard against than bases. So, you know, in the ketone bodies, if you don't eat very many carbohydrates, you make ketone bodies, or one of them is an acid, acetoacetic acid, yada yada. That's probably why, if you believe in that kind of thing, we were developed through whatever way you want to say to guard against acids more than bases. Let's do another problem, then we'll call it a day. Okay, what mass of sodium acetate would be required to add to 3 liters of 0.25 molar acetic acid in order to produce a buffer solution of pH 5.2? There's our weapon. pH, they gave us the pH, equals pKa. I can go look up that this is acetic acid, and actually we've already looked up the Ka of acetic acid. I might as well write it down. It is 1.8 times 10 to the minus 5, because we did it in the other problem. So Ka equals 1.8 times 10 to the minus 5. Let's go take inventory of what we got here. All right, what we've got here is our Henderson-Hasselbalch equation. pH equals pKa plus log, and in this case the conjugate base is C2H3O2 minus, and the acid is HC2H3O2. And now let's keep track of what they gave us. They said this was 0.25 in the problem. We can find this. They say we want a buffer that gives us a pH of 5.2. The only thing we're missing is that. Okay, we'll call it X. So let's go to work here and crank this out. So we'll go fill all this in. So 5.20, and then we got a little bit of an issue. We got 3 liters and not 1, so watch out. pKa is the minus log of 1.8 times 10 to the minus 5, which is 4.74. We did it in the other problem, but we'll keep going with it here. Plus log of X over 0.250. This is a solve for X problem, but let's keep going. 5.20. Now, if you remember from the last example, this was 4.74. We got an order of operations issue here. We got to get the log of X over 0.250 by itself. So let's subtract from both sides 4.74, and then we'll take a look at what we think we should be getting here before we go crank numbers. So that means that I'm paranoid and I got to do this on my calculator because I'm afraid I'm going to goof up. 0.46 equals log of X over 0.250. Now let's try to check ourselves before we wreck ourselves. I'm going to solve for X, but I know that because that number is greater than 0, 0 is what you'd get if these were equal. I know that X is going to be greater than 0.250. That means I'm going to have more base than conjugate acid, or more conjugate base than acid, and that makes sense because the pH is greater than the pKa. The pKa is where it would sit if you had equal parts. So we're going to have a little bit bigger than 0.25, or you just go trust your calculator and you do a 10 to the X of both sides, or an inverse log, I should say. And so 0.46 on the calculator, and then on the left, 2.88 is what happens when you do 10 to the 0.46. You get 2.88, and that makes sense. Should be between 1 and 10. 10 to the 0 would be 1, and 10 to the 1 would be 10. And what that does, this is also called an inverse log. Now that makes this just X over 0.250. And it feels like we're done, but we're not. Multiply both sides by 0.250. And 0.721 molar is the concentration of the acetate ion. And so let's finish this sucker off. This is moles per liter. Don't forget to go back and read the problem over again. So what I've got going on here is I've got 0.721 moles of Na C2H3O2. Per 1 liter. Oh boy, let's do the mole part first. 1 mole. Okay, count them up, huh? 22.99 is a sodium, plus 2 carbons would be a 12.01 plus a 12.01, plus 3 hydrogens at $1.01 apiece is 3.03. Plus 2 oxygens would be 32. This would be 82.04 grams. of Na sodium acetate. And don't be caught sleeping. They said it was going to be 3 liters. So, okay, let's see what that all is. 0.721 times 82.04 times 3. 177 point, how many digits was everything? 377 grams of sodium acetate. Didn't have to be sodium acetate, but that's what they said. Could have been potassium acetate, something that was a neutral ion acetate. So you go take that, add it to a 1/4 molar acetic acid. You divide, now maybe the volume would expand a little bit, but not much, because it would be more than 3 liters after you add it. But that thing would sit right at pH 5.20. And that's the skill level expert of problems right there. And you know, watch out you don't get crossed up with your logarithms, because when I was plugging in the wrong mode, it was telling me this is negative. I can't have negative moles per liter. And I had to go and put it on a different mode. But I still love my TI-30XA. Love it. Love it. It's a weapon for things like this. Okay, thank you for watching. Go enjoy, go out and get some vitamin D, and take care of yourselves, and we'll see you next time. Bye.